what if demand for kidney replacement therapy rose by X amount in the next couple of years, and then have the simulation run and produce those results for people. I think that would be really powerful, because I don't think we can underestimate the amount of other things people in the NHS have to do. So anything that we can do to make it easier for them to interact with tools that can help them is a win, and it's worth doing.
Welcome to Inside the Algorithm, the show that goes beneath the surface of artificial intelligence into the scientific research, technical breakthroughs, and academic thinking shaping where this technology is actually heading. I'm Jeremy Bradley, Chief AI Officer at Cambridge Spark, a leader in transformational data and AI upskilling, career development, and progression. Each episode, I sit down with the researchers, data scientists, and technical experts working at the true frontier of this field to explore not just what's happening in AI, but also the real science and thinking driving it forward. Whether you're building sophisticated AI systems, leading teams through AI transformation, or driven to understand what's really happening beneath the headlines, this is the show for you. In today's episode, we're getting into one of the most consequential applications of AI and operational research in the UK right now, the challenge of planning healthcare at scale inside the NHS. My guest today is Dr. Lucy Morgan, Head of Simulation at the NHS Strategy Unit, visiting researcher at Lancaster University Management School and 2025 KT Tocker Award winner for her work in simulation modelling. Lucy has led the development of a renal replacement therapy planning model that started with the Midlands Kidney Network and is now being rolled out nationally with ambitions to become a UK-wide planning tool by 2029. Her current research focus, as we'll hear, is model reuse and reproducibility, and specifically how AI could help build the trust and standardization needed to deploy analytical models across new organizations at scale. This is a conversation about what it really takes to make modeling work in the real world. I hope you enjoy it. Hello and welcome, Lucy. Thank you so much for joining us. I'm really excited to be talking with you today about your OR work and simulation work in the NHS Strategy Unit. You want to tell us a little bit about the Strategy Unit and what it does and sort of what how it operates?
Yes, so we're internal to the NHS, so we're all NHS staff. However, we're kind of a unit of our own, and we work across the NHS in a kind of consultancy way. Because we're internal, we don't make a profit, it gets put back into the NHS. So it's kind of a bit of a strange consultancy, because we are there to solve people's problems as a normal consultancy would, but it's almost in a slightly reversed way, where we try and create solutions that we can then use in multiple places, rather than making a solution and selling it to multiple people. So the ideas of model reuse and reproducibility and transparency and open science, open coding are really part of the Strategy Unit mantra. So I'm in the analytics and modelling team there, and heading up simulation, which is an exciting place to be. Yeah.
Nice. And they operate a model of backwards consultancy, I understand. So what does that entail in practice?
That's how I always describe it to people. But so when I think about making a model, I'm not just thinking about making a model for the trust or the part of the NHS that I'm currently working for. I'm trying to think, well, can we do this in a open and transparent way, such that if other areas want to use this model in the future, they could then come in, take that code, personalise the model to themselves, because the NHS is made up of many parts that look very similar. Like your A&E department in one trust will look very similar to an A&E department in another trust. They may function slightly differently, but not so differently that you couldn't adapt a model potentially to work across them. So that's the idea, to try and make something that we don't have to charge again for, or we don't have to keep reinventing the wheel and starting from scratch, to try and make more and more, basically making analytics as open as possible and as available as possible to other analysts working within the NHS. Because I find sometimes that they're analysts that are within trusts are working in kind of like a very siloed, that they're often working on their own. So if we can make things that they can use, it actually just powers them up to do more.
And then specifically, more recently, you've been working on a very contemporary topic of healthcare waiting lists in the NHS, and there isn't almost a month goes by without some discussion of NHS waiting lists for some operation or procedure or other. So this is a really important topic, but also quite a complex one as well. Do you want to give us a little bit more on what your work's been in that area?
I'd say that at the strategy unit, I kind of got into the waiting list area because a colleague of mine, Professor Mohammed, kind of when I first joined the unit, realised, oh, I've got a bit of background in operational research and simulation and queuing. So he brought me into to basically learn a little bit more about what he was already working on, which was to kind of orchestrate different efforts that were going on across the country in waiting lists. I got into it through that and then started working with academics at Durham University and other NHS staff down in Bristol. And we were looking at the problem of how many people do you need to remove from the waiting list, say every month or every year, to actually achieve the waiting list target that's been set, which is 18 weeks, basically. So 92% of the people waiting on the waiting list will have waited 18 weeks by the end of this parliament. So, I mean, we're nowhere near that at the moment, but we are moving in the right direction. So, yeah, it was a great starter problem, but it's not the only problem in waiting lists. And it ended up being, well, you could look at it as from a national viewpoint, like as a national waiting list, or down to specialty level. So there's the complexity there from there being many different problems to solve across many specialties, across many trusts, etc. So again, it's a problem of scale.
So queuing theory, which you're using to model these essentially very large virtual queues, they're not actually people standing in line. There are people just waiting at home, of course, and um, sometimes waiting many months, even years, to get to the top of the queue and get their operation. A really powerful technique for capturing these these challenges in any complex organization. Do you find there's a bit of a gap between using a theory like that to inform inform the process that, or inform a hospital, or the NHS around how many people should be removed from a list, and then how they actually then go about executing it?
Yeah, so I think what was done was a really important first step and really important question to answer. I mean, people want to know how to achieve the target, so the first thing you need to do is tell them how to get there. So how much relief capacity they need to give the system in order to move towards the target. So that is an important first question. Secondary to that is the almost operational question of, then, if I need to take 20 people off my waiting list this month, who on the waiting list do I need to take off? And that kind of brings in questions of prioritisation, um, deterioration whilst you're on the waiting list, because some people have been waiting a very long time. And it's not as simple as just taking those that have waited the longest off the list. There's some dynamics in there that mean that, there's definitely better ways to approach it than that. So that's where I feel like AI could really make some differences, or AI techniques, let's say, could be really powerful to not just look at how many people to take off, but how do we actually approach that, and on a daily basis or weekly basis, scheduling um, who should come in and when.
I'd like to sort of get a sense of what your sort of levers are here when you're making these sort of suggestions or adjustments to the queue, because I mean, as you say, it's not just a situation where you're saying we just want to take the first 10 people or the second 10 people. It's going to be sort of aligned to, well, this surgeon only carries out this type of procedure, so now we're limited to the first 3 or 4 people who can maybe be seen in a day, for whom that's applicable on the waiting list. And so there's an element of going down the waiting list and finding the people who actually match that procedure, for instance. But then, as you say, then there's an interesting sort of extra complexity around how difficult the procedure may be, how much time it will take, presumably things like how much time in recovery there'll be afterwards, and whether there are beds available for them there as well. Does that come into the equation?
Absolutely, like, the operational barriers are almost more important than the technical ones. I think you can come up with some really nice, uh, like, methods, and I've seen this. I was looking at it into it. There are trusts in the UK where AI is being used to do things like, prioritisation scores for patients on the list to try and understand who's, the highest priority to be brought in and for elective surgery next, etc. And it's even been used for validation, i.e., looking at people that have been waiting a long time and seeing who actually still needs the surgery. So there are really nice techniques out there that are looking at that type of thing. But then, yeah, as you say, your theatre capacity, or who's working when, those types of rotas, etc. It's the complexity is incredibly high, and often you find that the people making the decisions, i.e., the people that are like waiting list managers or actually they've got a lot of contextual knowledge that is hard to capture in a model. That, like, they know things because they've been doing it for such a long time. That kind of learning is something that is hard to replicate.
How do you find the data in this space? Because to get usable reinforcement learning approach in that area, classically you need, even for a tabular model, you need quite a lot of data just to be able to reasonably populate the decision and the reward table. And if you're using something that's neural network based, then even more data. So, what's your experience with getting good consistent data out of NHS trusts? Has that been an interesting conversation?
Well, I'm in a lucky position because we're within the NHS. We actually have got access to very granular data, often within the strategy unit. However, when you're an external, that's not the case. So I think that has been a barrier for sure. So some of these more interesting research gaps that are closing between academia and practice generally, because of NHS data being harder to access, it's harder to do that within the NHS. I think things are generally moving in the right direction on that front. But for what we're discussing here, it would need to be very local level data, and that would be quite hard to get a handle of. But and that's kind of why the approaches of, the queuing theory methods actually use open source or openly available data sets, like the referral to treatment data set, which is updated on a monthly basis by the NHS and published. So they've used what data they have available to use an appropriate technique to actually do something useful, which is good. But we need to go under the hood and much lower, more granular level to look at more granular techniques.
Speaking of really challenging problems, one of the other areas that you've been working on is area modelling kidney transplant processes. Do you want to tell us a little bit about the models and the problem area there?
This was actually the problem I was brought in to tackle when I joined the strategy unit. So, they had a relationship with Midlands Kidney Network, and the aim of the project was to look at trying to provide a holistic view of renal care, and that came in kind of two parts. So, I'm now a bit of a kidney expert myself, but just to highlight it overall, you basically end up on dialysis if you develop kidney disease, and that progresses to the point at which you get kidney failure. So we're going to model from chronic kidney disease through to end stage kidney failure, or end stage kidney disease, which is when you have dialysis. So we did a two-stage model, a sequential hybrid simulation model, which, if you've not heard of hybrid simulation models, they're just kind of a combination of different techniques. So we tried to think about the process we're actually modeling and match the simulation technique to the physical process that we were. So kidney disease is a continuous process. You are deteriorating over time, but you don't wake up one day and have a switch from stage 3 to stage 4, 5, for example. It's a slow deterioration, and therefore it suited us to use system dynamics, or it suited the problem to use system dynamics, which is a much more high level, population based, flow based methodology. And the kind of output of that model is the incidence of patients into kidney replacement therapy. So it projects how many people it thinks that over time are going to be coming through to actually needing dialysis and transplant. And then the second half of the model is actually, actual pathways of people living with kidney failure that need dialysis and need to be going into hospital, need a transplant and actually receive one, etc. So there's the two sides of the model that then fit together to give this view of capacity for kidney replacement therapy, which is something that is a little bit of worry in the NHS, because the need for people to be going on dialysis is growing and growing, and there needed to be intervention to actually control that capacity specifically for in-centre haemodialysis, which is where we're running out of space, I guess, for people in the future to be coming in and actually being treated. So what could they do? Could they prevent it earlier down the pathway, which is a pro of having this holistic view, or can they actually change people onto different types of dialysis, which is within the second part of the system, the actual kidney replacement therapy system? Yeah.
Gosh, constructing a model around that. I mean, I think it's difficult to underestimate how challenging and how difficult it is to get that kind of hybrid simulation of a complex system right. I'd like to explore that a little bit. So when you're talking about that population, that fluid element, which is describing the pathology, is it? The dynamic pathology of the kidney disease, that's more of a continuous sort of simulation, a continuous sort of representation of the progression of the disease. Is that do you have distributions of people with different dynamics? How does that side of it work?
So it's a stock and flow system. So there are a few stocks within the model, like undiagnosed stage 3 chronic kidney disease, diagnosed stage 3 chronic kidney disease, and the model effectively looks at the flow rate between the different stocks in the system. So you can progress having not been diagnosed, or you can progress having been diagnosed, and then there's the flow rate for actually having been diagnosed in the model. And there's I like how my colleague Sally describes system dynamics, because she thinks of it almost like as bathtubs where you're turning a tap on and off. And she describes the use of a medication that can slow the disease as almost like turning the tap so it's tighter, so you're not having a larger flow coming from one stage of the disease into the next. So there were different ways we could intervene within that system to kind of slow the flow through, and therefore the flow through into kidney replacement therapy.
And do you have data which then gives you some insight into how often people get diagnosed, so they sort of transition between the diagnosed and undiagnosed pathways across, depending on where they are in the progression of the disease?
Yeah, so there's a big study out there that's ongoing called CVD Prevent, which is like about cardiovascular diseases effectively. But within that, there's data on kidney replacement therapy chronic kidney disease also. So from there, we're basically able to understand at regional level or down to regional level how many people are approximately undiagnosed and how many are diagnosed. And from that, fit a model that we were then able to validate against observed numbers that are in chronic kidney disease. So there's a little bit of calibration needed within that model to kind of train it to produce reasonable results. And also, we were very lucky because we had experts working with us throughout that from Midlands Kidney Network. So yeah, clinicians are really deeply ingrained in the model.
I was going to ask then, naturally, as a data scientist, how did you go about validating against the data? What did the process look like? It sounds like you had fantastic support, so that's a really great start from subject matter experts. But but how did you use the data to then, give you that, this parameter, this flow rate, this is a good representation?
So for the kidney replacement therapy side of things, I mean, there's a really large literature on simulation validation. So we use standard techniques effectively, but they're not too different to how you'd train any algorithm. So when I was looking at the kidney replacement therapy system, I used data from 2010 all the way up to 2022 and looked at fitting all my input distributions with that, how long people were living with transplants and how quickly they were transitioning between different dialysis modalities, etc. Fit my distributions using those data, and then from 2022 onwards, looked at how well the inputs, the people flowing through the model represented what was going on in the actual system, to get a good fit, and then calibrate from there if necessary. But generally, we get a reasonably good fit to start with, unless there's a systematic change, which can happen in a system.
So you've got a low level fitting and then a higher level sort of system, almost system level validation based on the sort of population dynamics that you see. Is that right?
Yeah, effectively, yeah.
Nice. And then on the other side, you've got this much more granular, probably a simulation model I'd be more familiar with, more sort of discrete event process, which follows the stages of pathway treatment. Would that be? And then you've got a way of having the two simulations talk to each other. So how does that sort of play out?
At the moment, they are so one's a web app, chronic kidney disease. It's a toy you can actually go online. Anyone can access it and just look at the projections of what we think out to about 2035 is going to be the inflow of people coming into kidney replacement therapy. And then you can, at the moment, it's a little bit clunky, but you can basically just download that instance profile and put it into the interface of the other app and then run that forward through time. So we always have the baseline projection ready to be used within the kidney replacement therapy part of the model. But if you did an experiment in the earlier part of the model, i.e. prevention or more medication for people earlier in the pathway, you could take that instance profile and plug it in across. So at the moment, it would be lovely if that was seamless, but we are running out of budget for actually creating this. So that's something I'd like to do over time to improve things, but at the moment they are kind of two separate models that can talk to each other with a human involved.
One of the things you talked about at the start was being able to take a model, whether it's a queue model from the waiting list, whether it's for the kidney model that I think you worked on. You worked on the kidney model with one particular trust, and then trying to get the benefit of rolling it out. And that sounds like quite a challenging process. I know from personal experience that doesn't always work first time. Going to a different operation with different constraints potentially and different people involved. So how have you found that, and what's the pathway that you're observing there?
I'd say I'm still in the process of learning how to do this well. This is the first time I've ever taken a model and tried to take it to other areas and reuse it. But so the renal model that we've built is actually it's very, very similar in different regions of the country. The input models would need to be retrained on the data, but we have that data, so it feels achievable to actually take it to them, and we've started doing that now. We started in the Midlands, who were the people that commissioned the model, but we've rolled out to London and to the east of England, and there are other networks now that are coming on board. So we're hoping that we will reach the whole of England in the next year or so. But the problem is when we're going to other regions, they haven't been involved in the model building process. So where the Midlands were there throughout the workshops that we did a participative modelling approach where we had workshops where they were with us when we mapped the whole system, and they understood that we understood the system. So that there was the trust between the modeler and the client was effectively built, and then they also came with us through the validation process because we had workshops on that to show them this is why it works, this is why you should trust it. the other regions haven't actually had that experience, and it's almost that hurdle that I think is harder to bridge than the technical aspects of rebuilding the model for their specific contexts.
Do you see a role for AI, machine learning in supporting that bespoking process, or indeed that trust process, in terms of helping the regional managers believe that this is a really complementary service that you're developing?
I think that's where I'm really interested in research at the moment, like solutions that can help people understand models, almost question models. So I've had some conversations recently with academics at Exeter. So Professor Tom Monk's there. He's been looking at potentially using agents to allow people to question documentation and that type of um, approach, so that they could say, or even question a model, like, what if demand for kidney replacement therapy rose by X amount in the next couple of years, and then have the simulation run and produce those results for people. I think that would be really powerful, because I don't think we can underestimate the amount of other things people in the NHS have to do. So anything that we can do to make it easier for them to interact with tools that can help them is a win, and it's worth doing. But it will take development time, and I've not got a clear picture of how that's going to look or how it's going to work best at the moment. But that's why, yeah, actively trying to do research here. So
Do you have a call to arms here? It sounds like you're keen to use open tools and listen to the community and bring in expertise. Is there something you'd like from the community in that respect?
yeah, I'd love to hear how other people are going about model reuse, and creating reproducible models from start, like best practices. I've looked into this from a healthcare perspective, and I'm working with some really talented people that have are doing this. But I'm sure that it's used in other industries, and it would just be great to kind of share knowledge and see if we can learn from each other. So yeah, I'd love to hear from other people if they have had kind of experience in doing this, and they can maybe save me 2 years in the productionization/development cycles of what these products are whilst I learn. So
And I think as you get successful doing this, and no doubt you will, I think people will have a lot to learn from you, because vision of model portability is a real challenge to a large number of teams delivering in industry as well as in the public sector. So I think I really wish you all the best with that, because I think it's a fantastic aspiration, and it will save many lives, and enable many more treatments to happen. So that's a fantastic outcome. Thank you for listening to this episode of Inside the Algorithm. If today's conversation gave you something to think about, make sure you subscribe so you never miss a breakthrough, and share it with someone who'd appreciate the thinking. If you're a data and AI leader looking to build deep technical capability across your organization, Cambridge Spark is here to help. You can reach us on LinkedIn or at cambridgespark.com. And if you want to explore AI from the leadership and strategy perspective, check out our flagship show, Data and AI Mastery, with Dr. Raul Gabriel Irma. Until next time, stay curious, stay rigorous, and stay ahead of the algorithm.